In 1994, two giants battled for control of America's railroads as the industry demanded more power from fewer locomotives. EMD had dominated freight railroading for decades with their reliable DC traction technology, and the legendary SD-40-2. GE was the persistent challenger. Steadily improving their -8 series while developing revolutionary AC traction technology. By 1995, one locomotive would emerge that would fundamentally shift the balance of power in North American railroading. This is the story of how GE's AC 4400CW didn't just compete with EMD, it silenced their dominance forever. Electromotive division entered the 1990s as the undisputed king of North American freight railroading. The SD-40-2, introduced in 1972, had become the backbone of American freight operations with over 3,900 units built. This locomotive's combination of 3,000 horsepower, 6-axle design, and bulletproof reliability had created unprecedented fleet standardization across major railroads. The 40-2's success was built on EMD's 645 engine and proven DC traction motor technology. The 16-cylinder, two-stroke 645 E3 engine produced 3,000 horsepower at 900 RPM, while the D77 traction motors provided reliable power delivery that railroad maintenance crews understood completely. The locomotive's electrical system was straightforward. A main generator driven by the diesel engine supplied DC power directly to the traction motors through relatively simple control circuits. Fleet commonality was EMD's greatest advantage during this period. Railroads like Burlington Northern operated over 940-2s, creating enormous economies of scale in parts inventory, maintenance procedures, and crew training. A single railroad could maintain hundreds of identical locomotives with standardized procedures, minimizing training costs and maximizing parts availability. However, General Electric had been steadily closing the gap throughout the -8 era that began in 1987. The -840CW, introduced in 1989, paired the 4,000 horsepower 7 FDL16 with microprocessor-based controls that managed excitation, wheel slip, and auxiliaries, along with upgraded electrical systems that improved reliability and diagnostics over earlier GE models. GE's persistence in developing four-stroke diesel technology was beginning to pay dividends. The 7FDL engine offered better fuel efficiency than EMD's two-stroke 645, and the electronic controls provided diagnostic capabilities that simplified maintenance. The -840CW could operate for longer periods between major overhauls, and when problems occurred, the microprocessor systems could identify issues more precisely than EMD's analog systems. Railroad operating departments were demanding changes that would challenge both manufacturers. Trains were getting heavier as railroads sought to improve productivity, with coal trains routinely exceeding 15,000 tons and intermodal trains approaching 10,000 tons. These heavy trains required multiple locomotives, but adding more units increased crew costs and operational complexity. The solution railroads wanted was fewer, more powerful locomotives that could handle heavy trains without wheel slip or stalling on grades. Traditional DC traction motors had fundamental limitations in adhesion, the ability to convert engine power into tractive effort without spinning the wheels. When a DC motor began to slip, it would continue slipping until power was reduced, limiting the locomotive's ability to use its full power rating. Wheel slip was more than just an operational annoyance. It was expensive. Slipping wheels wore rapidly, requiring frequent replacement of expensive wheel sets. Slip events also damaged rails and reduced fuel efficiency as power was wasted spinning wheels instead of moving trains. Railroad mechanical departments calculated that reducing wheel slip could save thousands of dollars per locomotive annually in wheel and rail maintenance costs. Diagnostic capabilities were becoming increasingly important as railroads reduced maintenance staff and consolidated repair facilities. The analog electrical systems in EMD locomotives required experienced electricians to troubleshoot problems, and fault diagnosis often involved time-consuming testing procedures. Railroads wanted locomotives that could identify problems automatically and provide clear diagnostic information to maintenance crews. GE's answer to these challenges was the AC 4400CW, a revolutionary locomotive that incorporated AC traction technology developed from their industrial motor expertise. Introduced in 1993 for testing and entering production in 1994, the AC-44 produced 4,400 horsepower from the proven 7FDL16 engine, while using AC traction motors that fundamentally changed how locomotives converted power into tractive effort. The heart of the AC-44 was its AC traction system, which used inverters to convert the locomotive's DC electrical power into variable frequency AC power for the traction motors. Each traction motor was controlled by its own inverter, allowing precise control of motor speed and torque that was impossible with DC systems. The inverters used gate turnoff thyristor GTO technology to create variable frequency AC for each traction motor, enabling precise control of torque and speed. The AC traction motors themselves were three-phase induction motors that operated on completely different principles than DC motors. Instead of using brushes and commutators like DC motors, the AC motors used electromagnetic fields to induce rotation in the rotor. This eliminated the brush maintenance that was a constant requirement with DC motors and allowed the motors to operate at much higher power levels without overheating. The adhesion advantages of AC traction were dramatic. When an AC motor began to slip, the inverter could instantly reduce power to that specific motor while maintaining full power to the other motors. This individual motor control meant that the locomotive could use nearly 100% of its rated power without wheel slip, compared to DC locomotives that typically could only use 75 to 80% of their power before slipping occurred. The AC-44's continuous tractive effort rating was 166,000 pounds compared to just over 83,000 pounds for EMD's SD-60, despite both locomotives weighing approximately the same. This meant the GE locomotive could pull twice as hard at low speeds without slipping, making it ideal for starting heavy trains and climbing steep grades where wheel slip was most problematic. GE designed the AC-44 specifically for large fleet operations, incorporating features that would appeal to railroads operating hundreds of identical locomotives. The locomotive's modular electrical system used standardized components that could be quickly replaced, while the microprocessor controls provided comprehensive diagnostic information that simplified troubleshooting and maintenance planning. The 7FDL16 engine in the AC-44 incorporated lessons learned from decades of four-stroke development. Electronic fuel injection provided precise fuel delivery across all operating conditions, while the engine management system optimized performance for fuel efficiency and emissions compliance. The engine could operate for 92 days or 25,000 miles between major inspections, significantly longer than EMD's two-stroke engines. CSX Transportation became the first railroad to field the AC-44 in regular Class 1 service in 1994, ordering an initial batch of 25 units for evaluation in coal service between West Virginia and Virginia. These locomotives were assigned to the heaviest coal trains on CSX's system, where their adhesion advantages could be fully utilized and evaluated against existing EMD power. The early results were impressive enough to spark immediate interest at other railroads. CSX reported that single AC-44 units could replace pairs of SD-40-2s on many coal trains, reducing crew costs and improving operational flexibility. The locomotives could start 15,000-ton coal trains on 1.8% grades without helper locomotives, something that required multiple DC units or additional helper power. More importantly, the AC-44s demonstrated remarkable consistency in their performance. Unlike DC locomotives that might perform differently depending on rail conditions, weather, and wheel wear, the AC units delivered predictable tractive effort regardless of operating conditions. This consistency allowed dispatchers to plan train operations more precisely. Canadian Pacific's decision to order AC-44s in large quantities during 1995 proved that AC traction was ready for mainstream adoption, not just experimental service. CP ordered 133 AC-44s in their initial purchase, the largest single order for AC locomotives at that time. This order demonstrated that a major railroad was willing to bet their operations on AC technology. CP's order was particularly significant because it came from a railroad known for conservative locomotive purchasing decisions. Canadian Pacific had been primarily an EMD customer for decades, operating large fleets of 40-2s and 60s. Their decision to switch to GEAC power reshaped the locomotive industry and signaled that AC traction had moved from experimental technology to a proven solution. The Canadian Pacific locomotives were assigned to grain service between the Prairie provinces and Vancouver, where their ability to handle long, heavy trains over mountain grades provided immediate operational benefits. CP reported that AC-44s could handle 8,500-ton grain trains over Rogers Pass with 2 units, compared to 340-2s required for the same trains. Union Pacific also began evaluating AC-44s in 1994, initially ordering 50 units for testing in coal service from Wyoming's Powder River Basin. UP's coal trains were among the heaviest in North America, routinely exceeding 15,000 tons, and the railroad was looking for ways to reduce the number of locomotives required per train while maintaining schedule reliability. The operational advantages of AC traction became clear as railroads accumulated experience with the AC-44 in regular service. The higher adhesion meant that fewer locomotives were needed for heavy trains, reducing both capital costs and operating expenses. A typical 15,000-ton coal train that required 4 SD-40-2s could be handled by 3 AC-44s, representing a 25% reduction in locomotive requirements. The adhesion advantages were most pronounced in challenging operating conditions. On wet rails where DC locomotives might slip continuously and require reduced power, AC locomotives maintained full tractive effort without wheel slip. This meant that trains could maintain schedule even in adverse weather conditions that would slow or stall DC-powered trains. Continuous tractive effort capabilities eliminated many of the helper locomotive requirements that added operational complexity and cost. The AC-44 could maintain 166,000 pounds of tractive effort from 0.5 to 11 miles per hour, compared to DC locomotives that could only maintain maximum tractive effort at very low speeds. This extended high tractive effort range meant that AC locomotives could pull heavy trains up long grades without stalling or requiring assistance. The duty cycle economics were compelling for railroads focused on reducing operating costs. Fuel consumption per ton-mile improved because AC locomotives could operate at higher power levels without wheel slip, eliminating the fuel waste associated with spinning wheels. Norfolk Southern reported fuel savings of 8 to 12% when replacing SD-40-2s with AC-44s in coal service. Wheel wear reduction provided another significant cost advantage. CSX reported a 40% reduction in wheel replacements with AC power versus DC, saving thousands per locomotive annually in wheel costs and shop time. The microprocessor-based control systems provided diagnostic capabilities that revolutionized locomotive maintenance. The AC-44's computer systems continuously monitored engine performance, electrical systems, and mechanical components, storing fault data that maintenance crews could access through handheld diagnostic tools. This eliminated much of the guesswork involved in troubleshooting locomotive problems. Fault diagnosis that might take hours with analog DC systems could be completed in minutes with the AC-44's digital systems. The locomotive's computers could identify specific failed components, predict impending failures, and provide maintenance recommendations based on operating history. This predictive maintenance capability allowed railroads to schedule repairs during planned maintenance windows rather than dealing with unexpected failures in service. The standardized diagnostic systems also simplified maintenance training and procedures. Instead of requiring experienced electricians who understood the nuances of different locomotive electrical systems, railroads could train technicians to use standardized diagnostic procedures that worked consistently across entire fleets of AC-44s. The success of the AC-44 created a cascade effect that fundamentally shifted locomotive procurement patterns across North American railroads. The orders in the mid to late 90s increasingly favored GE's AC technology, with major railroads placing orders for hundreds of AC-44s as they experienced the operational benefits firsthand. BNSF, formed by the 1995 merger of Burlington Northern and Santa Fe, became GE's largest customer with orders for over 1,000 AC-44s between 1995 and 2004. BNSF's decision to standardize to AC power for their coal and grain operations created enormous scale effects that locked in GE's advantages in manufacturing costs and parts availability. The scale effects worked against EMD as GE's production volumes increased. Higher production volumes allowed GE to negotiate better prices with suppliers, invest more heavily in manufacturing automation, and spread development costs across larger numbers of units. These advantages made GE locomotives increasingly competitive on price while maintaining their technological superiority. EMD's response with the SD60 and early SD70 series looked incremental compared to the revolutionary change that AC traction represented. The SD60, introduced in 1984, offered 3,800 horsepower from an improved 710 engine. But it still used conventional DC traction motors with their inherent adhesion limitations. The SD70, introduced in 1992, provided 4,000 horsepower, but remained fundamentally a DC locomotive competing against AC technology. EMD's high horsepower, 265H engine and SD90 Mac H locomotives absorbed significant engineering resources and management attention during the mid-1990s, but these programs were troubled from the start. The 265H engine suffered from reliability problems that damaged EMD's reputation, while the SD90H's 6,000 horsepower rating proved to be more than most railroads needed or could effectively utilize. The SD90 Mac H program's problems diverted resources from developing competitive AC locomotives, allowing GE to establish an insurmountable lead in AC technology. While EMD struggled with the 265H engine, GE was refining their AC traction systems and building the manufacturing capacity needed to meet growing demand for AC-44s. Canadian National's decision to purchase 320 AC-44s between 1996 and 1999 demonstrated that AC traction had become the preferred technology for heavy freight operations. CN's order was particularly significant because it represented a complete fleet renewal program based on AC technology, replacing older EMD power with standardized GE units. Union Pacific's massive orders for AC-44s, totaling over 1,000 units by the year 2000, cemented GE's position as the dominant locomotive manufacturer. UP's decision to standardize on AC power for their coal operations created the largest single fleet of identical locomotives in North America, providing unprecedented economies of scale in maintenance and operations. By the decade's end, locomotive procurement had tilted decisively toward GE and AC traction technology. The AC-44 had proven that AC motors could provide significant operational advantages over DC technology, while GE's manufacturing scale and technological leadership made them the preferred supplier for major railroads. The transformation was complete when even traditionally EMD-loyal railroads like Norfolk Southern began purchasing AC-44s in large quantities. NS ordered 200 AC-44s in 1999, acknowledging that AC technology had become essential for competitive freight operations. EMD's market share declined from over 70% in the early 1990s to about 30% by 2000, a dramatic reversal that reflected the industry's embrace of AC traction technology. The company that had dominated locomotive manufacturing for over 50 years found themselves playing catch-up to a competitor that had successfully revolutionized railroad motive power.